All right, in this video, I want to address the following question. Does parameterization matter for scalar line integrals? Okay, so if you think about the problems that we've solved up to this point, we've said, okay, here is your path, and let's write down a parameterization for the path, and then we'll use that parameterization to compute the line integral. Okay, however, okay, there are various ways to parameterize a given path. Okay, so is it possible to say parameterize the path in one way, compute the integral and get a value, but then you parameterize the path in another way, compute that corresponding line integral, and you get a different value? Or are the values always going to come out to be the same? That's what we want to answer in this video. Okay, so to illustrate, let's take the function f of xy is 2x squared plus y, and we're going to take the line integral of this function over the unit circle. And so to start, I'll go ahead and parameterize the circle by letting x equal cosine t and y equal to sine t, and we'll let t vary from 0 to 2 pi. So we're going to plug in cosine t for x to get 2 cos squared t, and plug in sine t for y to get plus sine t. Now, ds will just equal dt here because the derivative vector, which is minus sine comma cosine, that has unit length. And you're going to integrate this expression from 0 to 2 pi, winds up turning out to be 2 pi for the value. Okay, so then you say, all right, what would be another way to parameterize this circle? Well, what if I say set x to sine and y to cosine? Okay, now my integrand will be 2 sine squared t plus cosine t. Again, ds will come out to be dt. We're going to be integrating now over this circle as we move clockwise, and we're going to make one complete trek around as we let t vary from 0 to 2 pi. So integrating this expression from 0 to 2 pi does turn out to come out to the same value, right? 2 pi. Okay, so you might say, oh, maybe that's just luck. Okay, what would be another parameterization? Okay, here's another one. How about letting x equal sine 2t and y equal to minus cosine 2t? Okay, so notice by sticking this 2 in front of the t, I'm now going to make a trek around the circle in just pi units as opposed to 2 pi units. So I'm speeding up. And I'm letting t start at negative pi over 2, in which case I'd be at the top of the circle. And then I'm going to walk counterclockwise and make one complete trek as t varies from minus pi over 2 to pi over 2. Okay, now plugging in, we get 2 sine squared 2t minus cosine 2t. Now ds here is not just dt in this instance. If I differentiate, I'm going to pick up a factor of 2 from the chain rule, so I'm actually going to get a 2 dt. Okay, remember that 2, the magnitude of the derivative, that's really our speed. And so that 2 coming out is just an expression of the fact that we're now running around our circle twice as fast. Okay, but nonetheless, with all of that, you integrate and you do wind up getting the same value of 2 pi. Okay, so these examples here at least suggest that, hey, maybe it doesn't matter how you parameterize the circle. Maybe you're always just going to get the same value. And it turns out that that is the case. Okay, it can be proven that scalar line integrals are independent of parameterization, meaning that if you parameterize your path C in one way, and you compute the corresponding line integral, and then you parameterize the path in another way, and you compute that corresponding line integral, those values will come out to be the same, which is quite nice, right? It basically is telling you, hey, just come up with a parameterization. You don't have to worry about how exactly you are parameterizing it, okay? So in the next video, we're going to introduce vector line integrals, where parameterization is just more of a sensitive issue, and we will start unpacking that all coming up next. So I will see you there. All right, thanks.